Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we'll go through groups. So groups has a colloquial meaning, just, few people together make a group, but we have a very special and precise definition of a group in maths. So it's important to note that when we're talking about a set being a group, it needs to have some operation that we refer to. So that operation could be addition, multiplication, subtraction, exponentiation. It could be permutations, compositions of functions, whatever. So it's important because a set will form a group under some operations but not under others. So under that operation, the set has to be closed. That's the first axiom. It has to be associative. That's the second. Third, each element has to have an inverse under the operation. And fourth, the identity needs to be a member of the group. So I'm going to explain what each of these axioms actually means. So just to get some notation, I'm going to let G for group equal the set that we're going to refer to. And remember, if I say something like X is in G, that means X is a member or an element of G. Because the operation can be so many different things, as I alluded to before, I'm just going to call it little o. That will be the operation to which I refer. So I'm going to go through now and explain what each of the axioms mean. So the first one, what does it mean if the elements are closed? The set is closed under the operation. What it means is if you perform the operation on any two members of the set, you get another member of the set. So formally, I can say if X and Y are elements of my set G, then that means when I perform the operation on them, the result will also be in G. So, associative, you would have learned what this means in year 7. So what it means is if you have three elements now, so I'm going to call them X, Y, Z, all elements of G, you can sort of group the operation any way you want. So if I want to operate all three, it doesn't sort of matter where I put the brackets and which I do first. So I can put the brackets here, or I can put the brackets there. That's what associative means. So in the first one, I've grouped X and Y together. In the second, I've grouped Y and Z together. Now, please understand, associative is not the same as commutative. Associative is not saying that the order doesn't matter. It's about being able to group elements together when you're performing the operation on many of them. Okay, there's no requirement for a group operation to be commutative. So third, each element has an inverse. So let's write that formally. So that means if X is an element of G, then its inverse, so I'm just going to call it X inverse, is also an element of G. So even though X to the power minus 1 usually means multiplicative inverse, I'm just saying the inverse under whatever the operation is. So if the operation was addition, X inverse would refer to the additive inverse. So the last one is that the identity for the operation is a member of the set. So I'm just going to call that E for identity. So again, remember the identity was slightly different depending on the operation. There is a different additive identity than multiplicative identity. So again, the operation does not need to be commutative. And commutative, again, means that the order does not matter. So an operation is commutative if X operation Y is the same as Y operation X, okay? So you're used to addition and multiplication being commutative because the order doesn't matter. But the operation we're talking about isn't required to have that property. It isn't required that the order doesn't matter for that operation to help form a group, okay? So if the operation we're talking about satisfies all of these axioms and it is commutative, then it is called an abelian group. So let's look at an example of a group or some non-groups as well. So hopefully this will make these axioms clearer. So let's look at our set of real numbers again. So that includes all the numbers, all the integers, all the fractions and rational numbers, all the irrational numbers like pi, square root 2, square root 3, whatever. So the real numbers just includes all the numbers that you know. So let's determine whether or not it's a group. Now, it's really important that you specify not only the set, in this case real numbers, but the operation. It turns out that the real numbers forms a group under addition, but not any of the other of the four operations. It does not form a group under subtraction, division, or multiplication. So I'm just going to write it like this. This means the set of real numbers under addition. Okay? So it forms a group. Let's look at the axiom. So the first one. Are the elements closed under addition? Yes, because when you add together any two real numbers, you get another real number. So 1 is satisfied. Let's look at the second one. Is the operation associative? Yes, addition is associative. So 3. Does each element have an inverse under the operation? Yes, because the additive inverse of A is just minus A. So the negative of a number, the opposite of a number, is also a real number. So 2 is a real number, so is negative 2. Half is a real number, so is negative a half. So each element has its inverse, its additive inverse, as a real number. So 4, the identity is a member of the set. Well, yes, definitely. 0, the additive identity is a real number. So the real numbers under addition satisfies all four axioms, therefore it's a group. Now, as I said before, addition is commutative. A plus B is the same as B plus A. So not only do the real numbers form a group under addition, they form an abelian group under addition. So how would you actually prove that the real numbers form a group or an abelian group under addition? Well, you can't really prove it because most of these group axioms for the real numbers are axiomatic. So what I mean by that is, so how do we know that the set of real numbers are closed under addition? Well, that is just an axiom of the real numbers. Same with associativity, for example. So what I'm getting at, there are axioms, not just of groups, but of the real numbers. And they are things, statements that we say, yes, they're true, without proof. And they sort of form the starting point for all of maths. So you can't really prove that the real numbers are, say, associative under addition, because that is just something that we said, yes, this is true. That was our starting point. But what it does mean, of course, is that any subgroup of the real numbers will also be associative under addition. So if you just looked at the integers or the irrational numbers or the rational numbers, they would also be associative because of that axiom. So you can't really prove that the real numbers form a group under addition. It is axiomatic. It's just because of the axioms of real numbers. So let's look at the real numbers under other operations. So let's look at the set of real numbers under, say, subtraction. So this actually does not form a group. So why does it not? Well, the first axiom satisfied. If you subtract any two real numbers, you get another real number. So that's fine. But the second one actually fails. So to give you an example, if I have, let's say, 10 minus 4 minus 3, if I change where the brackets are, it will give me a different answer. So if I put the brackets here and group the first two, I get 6 minus 3, which is 3. But if I put the brackets here, I get 10 minus 1, which is 9. Subtraction is not associative. It turns out the third and the fourth axioms are satisfied. Each element does have an inverse under subtraction, and the identity for subtraction is the same as the identity for addition, is 0. That's a real number. But because just one of the axioms is not satisfied, it is not a group. So if I looked at the real numbers under multiplication, it sort of almost forms a group. So if I'm looking at real numbers under multiplication, the only thing that fails, each element has an inverse. Well, actually 0 does not have an inverse. You can't multiply 0 to get 1. So that's the only thing that fails. So it actually turns out that all the real numbers except for 0 form their own group, but you can't say that the real numbers form a group under multiplication because there's one number that does not have an inverse. So if you wanted to look at the real numbers under division, well, actually quite a few of them are not satisfied. So the first one isn't satisfied because if you divide by 0, it's not a real number. 4 divided by 0 is not a real number. So that isn't true. Division is also not associative. So each element has an inverse under the operation. Again, 0 presents a challenging case. You can't divide 0 by a number to get 1 because 1 is the identity for division. So the real numbers do not form a group under subtraction, multiplication, or division, but they do form a group under addition. So we can use the properties of groups to be able to prove things about groups. So I'll just show you a quick example of this. So we're going to look at proving this proposition that in any group, the identity for a given operation is unique. So note this is saying for a given operation. So of course, in a group, you might have the additive identity and the multiplicative identity being different, but you can't have two multiplicative identities that are different in the same group. You can't have two additive identities in the same group. If the operation was composition of functions, you can't have two identity functions in the same group. That's what it's saying. So let's look at how we would prove this. My first step needs to be able to formulate these words from the proposition into some sort of mathematical writing. I need to formulate it mathematically. So what I'm saying, if the identity is unique, is that there can't be two of the same identity. So I'm saying that if there are two of the same identity, if there are two identities under a given operation in a group, they must be equal. So I'm going to start off by defining the operation because I need to know which operation I'm talking about. And then I've written what I just said. So I want to prove that if E and I are both the identity under an operation, then they must be equal. They must be the same element because the identity is unique. So it's important that I know what I'm trying to prove, that I get to something that looks like an equation. Because that's how we prove things in maths. We're proving things by using equations. We're not proving things by just proving words. So I want to prove that E is equal to I, okay? So now I'm going to start the sort of arithmetic by using what I defined E and I as. I define them as identities. So what does it mean if something is identity? So what I'm going to do is I'm going to let G be a member of the group. So I told you at the start it is a group. So I need to formally write what does it mean if E and I are identities? Well, if E is an identity, it means that E, if I operate on G, it just gives me G. And similarly, I, if operated on G, it gives me G because I is an identity. So what this actually means is, because this and this are equal, I have that E operated on G is the same as I operated on G. But because this is a group, so this is where I rely on the fact that it's a group, if G is a member of the group, so too is G inverse. So G inverse is a member of the group as well. So what I can do is I can take my equation here and I can operate each side by G inverse. So what I have is E operated G operated on G inverse is equal to I operated on G inverse. Now, Because this is a group, the operation O must be associative. Otherwise, it would not form a group under that operation. So remember, associative means I can group the elements as I want. Essentially, I can put the brackets wherever I want. So I've got my equation, and I'm going to group them like this. I can do that without changing the value of either side of the equation. But of course, G, when it is operated with its inverse, just gives the identity. So what I have here is that E times the identity, because that's what's in the blue brackets, that gives the identity, that just gives me E. But on the other side, I have I operated with the identity, because this in brackets is the identity. So what I'm left with is E equals I. So if E and I are identities, then they must be the same thing. So that means the identity is unique, because if you have an identity and there's another element that's the identity, then those two must be equal. There can only be one identity in a group under any operation. So this proves it for any group and for any operation because I used arbitrary elements. Because I have that the operation O could have been any operation. It could be addition, multiplication, whatever. This same logic and same proof works. Similarly, because I used E, I, and G, they can be any numbers, any elements of the set, and this logic will work. So this has proved it for any group and for any operation. All right, sorry for the long video. I hope you've enjoyed it. This has been the luckiest maths teacher in the world. Have a great day.